The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you all are doing good and busy with your preparation for your online exam. In chemistry, we have two chapters, chapter 5 and 6. So I would like to say chapter 5 we have most of the theory part, and chapter 6 of course there are few reactions, and you just have to concentrate on the theory part more when compared to that of reactions in these two chapters. Okay, so write and practice, and if you have any confusion please ask me, children, no problem. Don't think what the teacher will feel. Definitely your confusions or in your doubts must be clarified then and there. Okay, see, we have come to the last part of the 7th chapter, P block elements. Last class we were learning about sulfur. Especially when this chapter is concerned, you have lot of reactions, preparations which will not change. So definitely you have to learn it by heart. Okay, so today we are going to study about 17th group elements. We have been seeing the periodic table right from our 8th standard, and especially from 9th standard we have just focused on representative elements and other things. So here P block, again representative elements, in that the 17th group are called as halogens. Halo means salt and gens means producers. So they are called as salt producers, or you can say they will be most probably present in the salt content, that is wherever the source has got salt you can see these elements present. They are very highly reactive and they are non-metallic in nature, and if you see fluorine and chlorine, they are very abundant, means they can, as fluorspar, calcium fluoride, you can see especially in sea water and river water plants wherever they are available. And when you come to the electronic configuration, that is the general trend, they have Ns2Np5, that is S subshell completely filled and P subshell with 5 electrons in the P subshell, because they need 1 electron more to become a noble gas, to attain the noble gas configuration, because we know 18th group is a noble gas and 17th group is a halogens. So they just need only 1 electron to become an octet configuration. And when we come to atomic and ionic radii, when you go along the period, this we have been discussing for many classes, when you grow across the period, what happens? Only the electrons get added but the shell remains the same. I was explaining you about the screening effect, that is, this is my nucleus, I have my first orbit, second orbit, third orbit. Now the electrons which are present in the last orbit will be not getting the nucleus attraction. Why? Because of the electrons which are present closer to the nucleus. The nucleus is there is one shielding of the nucleus, that is the outermost electron are not getting the nucleus effect. So that we called as effective nuclear charge. So what happened when you go across the period, the effective nuclear charge is more, or you can also say the nucleus attraction towards the outermost electron, again when it is only the electrons are getting added, not the shells. So when they attract the electrons which are negatively charged, the size of the atom actually shrinks. That's why we say the atomic and ionic radii, it decreases across the period and it increases down the group, because when we go down the group, the number of shells actually increases along with the electrons. Now when we come to ionization energy, see they have a very high ionization energy. What could be the reason? I told you these are 17th group and our 18th group is noble gas. Since they need only one electron to become octet, their tendency to lose the electron is very less. They don't like to lose electron. Instead, they want to gain electron to attain this noble gas configuration. So what happens? Since the tendency to lose is very less, their ionization energy will be very high. They are not ready to give the electron. So they keep the electron within the atom, that is within the orbit. So you need to put more energy to remove the electron. So in order, we will say they have a very high ionization energy. Now when we come to electron gain enthalpy, they have the maximum electron gain enthalpy. The reason is the same again, it needs only one electron to become octet. So that one electron makes it more and more getting attracted to gain the electron. And this one electron less than the noble gas makes maximum electron gain enthalpy. In that, fluorine has got less electron gain enthalpy when compared to chlorine, only just because of its small size. Compared to chlorine, fluorine has a very small size. And when we come to electronegativity, again we know the 17th group elements are the most electronegative elements in the periodic table, out of which fluorine is the most electronegative element in the whole periodic table, and that electronegativity decreases when we go down the group. And when we come to physical property, you have solids, liquids and gases. Fluorine and chlorine exist as gases, bromine as liquid and iodine as solid. And they have a tendency to absorb the radiation and also emit the radiation. So you can see most of the halogens, they are colored. Like fluorine is yellow in color, chlorine is greenish yellow, bromine is red and iodine is actually violet in color. So these are the general trend of the properties. Now we will get back into chemical properties, thereby studying the anomalous behavior. Okay. Okay, let's see the chemical properties of this halogens. If you see halogens, generally they need only one electron to become octet. So that will be -1 because electron has been accepted. So they have a -1 oxidation state in general. But if you see chlorine and bromine, iodine, they also exhibit positive oxidation state like +3, +1, +5 and +7, which means they have a tendency even to lose electrons. Now how does this happen? This happens only when the halogens react with the halogens only, again to lose electrons and gain a positive oxidation state like forming interhalogens, oxides or oxoacids. When they form all this, because when they react with fluorine, or when chlorine is reacting with fluorine or chlorine reacting with bromine, definitely one of the halogen should be having a positive oxidation state. Now how does this happen? If you see, they have Ns2 and Np5 electrons. So this is in the ground state. Now what happens here? If you see, there is only one unpaired electron in one of the orbital of the p subshell, which means they can show +1 oxidation state. Now what happens here? Assume that the second orbital 2 electrons are there, out of which one will be shifted to the d subshell. So how much you will be getting is 3 unpaired electrons, so having +3 oxidation state. The next level, what happens? After this state, again in the p subshell there is 2 electrons, so out of which 1 electron will be jumping to the orbital in the d subshell. So you have 1, 2, 3, 4, the 5th electron jumps here. So you will have 5 electrons, so +5 oxidation state. In the last stage, 2 electrons in the s, one of the electron will get into the d subshell, so it will be 1, 2, 3, 4, 5, 6, 7. So that's how the 7 electrons are lost, having a +7 oxidation state. So because of this general reason, halogens also show positive oxidation state. We were discussing about oxygen having +1 and +2 oxidation state. Similarly, when they have a tendency to react with electronegative elements, halogens tend to become electropositive by losing the electrons. Now if you see fluorine compared to other elements in the halogen family, fluorine do not have any d orbital, so it cannot expand its octet. Just like our nitrogen, we were saying there is no d orbitals. So it always have a -1 oxidation state, that is accepting one electron and attaining a noble gas configuration. Now this halogens, they have generally a tendency to react with metals and non-metals, giving halides. If you see, they react with sodium metal to give sodium chloride, magnesium to give magnesium chloride, aluminium gives AlCl3. If you see with non-metals like carbon, it gives carbon tetrachloride, right. So they have a tendency to react with metals and also the non-metals, giving the corresponding halides. And peculiarity is they have a very good oxidizing property, that is they tend to oxidize the halide ions themselves by interchanging the ions, that is Br2, when it reacts with iodide ion, it becomes bromide ion and liberates iodine. So this is how it tends to become an oxidizing agent. Now how this oxidizing property is being confirmed, that is it shows, is just because when it is soluble in water, if you see fluorine, when it reacts with water, it tends to give oxygen gas. Same the chlorine and bromine, when they react with water, it gives HCl, HOCl, or I can say HBr and HOBr. So that is why the trend is that shows that fluorine is somewhat having an exceptional character or exceptional behavior when compared to other halogens in the halogen family. So now we will learn about the anomalous behavior of fluorine with respect to different reactions. Anomalous behavior of fluorine. Now fluorine has high ionization energy, electronegativity and electrode potential when compared to other elements in the halogen family, that is comparatively very high values when compared to chlorine, bromine and iodine. And what about the ionic radii, melting point, bond dissociation enthalpy and boiling point are extremely in low range when compared to the elements in the halogen family. So because of these reasons, fluorine has an exceptional behavior when compared to the other members in the halogen family. Now what are the 4 main reasons that contribute to the fluorine's anomalous behavior are its small size, fluorine having extremely small size, very high electronegativity, low FF bond dissociation enthalpy. What is bond dissociation enthalpy, children? Bond dissociation. Dissociation means breakup. So the fluorine bond, when it's going to break, the energy required to break the bond is very less. So because of its very low FF bond dissociation enthalpy, it shows an exceptional behavior. And also because of non-availability of the d orbitals. So I repeat, small size, high electronegativity, low FF bond dissociation enthalpy and non-availability of d orbitals are the 4 main reasons for the anomalous behavior of fluorine. If you see the general reactions of halogens towards hydrogen, oxygen and other metals or also with their halogens are this halogen, any halogen that you take, when they react with hydrogen, they form the corresponding hydrogen halide. Like hydrogen plus chlorine gives HCl, with fluorine gives HF, with bromine gives HBr. But that hydrides, the formation of the hydrides actually decreases when you go down the group. Tendency to react with hydrogen decreases down the group. The hydrogen halides once formed, when it reacts with water, it forms the corresponding hydrohalic acid. Like when I say HCl, when it reacts with water, it forms HOCl. When HBr reacts with water, it forms HOBr. So these are the tendency for the hydrogen halides to get immediately dissolved in water to form the corresponding hydrohalic acid. And when you see the acid strength of all the hydrogen halides, HI has got the highest acidic property when compared to HBr, HCl and HF. So because of this trend in the acid strength, their stability actually decreases when you go down the group. The stability of the hydrogen halides decreases down the group because the bond dissociation decreases, because we know FF bond is very less, and when you go down, what will happen when you compare to the other elements? So with which HF is having the highest and HI is having the lowest. So these are the main thing when compared to the other elements. It is when you take only halogens with hydrogen reactions. Now we will go with oxygen, metals and halogens, that is forming interhalogen compounds. Reaction with oxygen, metals and halogens. If you see the halogens, they react with oxygen to form the corresponding oxides, of which most of the oxides, they are actually unstable, they tend to react immediately. If you see fluorine, it forms two type of oxides, OF2 and O2F2, out of which OF2 is thermodynamically stable, and we know fluorine is being more electronegative than the oxygen, and so both can be used as fluorinating agents. Other than fluorine, if you see chlorine, bromine and iodine, they tend to react with oxygen, having different compounds, variety of compounds with oxidation states ranging from +1 to +7. Because in the previous slide I was discussing you about how the halogens were exhibiting the positive oxidation state when they react with more electronegative element. And higher oxides are more stable compared to the lower oxides of the halogen family. Some of the oxides are Cl2O, ClO2, Cl2O6, Cl2O7, we have BrO3, Br2O7, I2O5, IO3. So many oxides are available, in which ClO2 is commonly used as a bleaching agent, I2O5 or their compounds are used as oxidizing agents, and also bromine compounds of oxides are also used as oxidizing agents. And their reactivity with metal, they react with ionic compounds, especially with metals, to form their corresponding halides, like magnesium and bromine giving magnesium bromide, sodium and chlorine giving sodium chloride, but their ionic character actually decreases down the group, which means fluorine will be having the maximum ionic character with the compound that it is formed, that is with metals, as compared to chlorine, bromine and iodine. Now the last part is reacting with their own members in the family, that is a halogen reacting with another halogen, in which I have mentioned XX dash, XX dash 3, XX 5, XX 7, which means where X represents a large size halogen and X dash represents a small size halogen, where it can form ICl2, IBr2, BrI2. There are different types of intrahalogen compounds formed, which we have a separate topic about preparation of intrahalogen compounds and their properties. So now we will learn about chlorine, then we will go to HCl and then the oxides. Chlorine. Now this compound chlorine was discovered by Skill. He was a scientist in the year 1774 and he had many preparations of preparing chlorine, and we know chlorine and fluorine, they exist as gases. So the first preparation was from manganese dioxide. Manganese dioxide, when it was treated with hydrochloric acid, it gives manganese chloride, water along with chlorine gas. So you use an upper headed arrow to show the gas. So chlorine is obtained in the gaseous form. Another preparation is treating hydrochloric acid with potassium permanganate. Again you get potassium chloride, manganese chloride, water and chlorine gas being liberated. Now these are the basic laboratory preparation. Apart from that, in the manufacturing process, it had two methods of preparation. First one is Deccan's process, the other one is electrolysis. In Deccan's process, hydrochloric acid or hydrogen chloride is being burnt, or you can say it undergoes combustion or combines with oxygen in the presence of copper chloride as catalyst, CuCl2 as catalyst, to form chlorine gas, where chlorine gas will be collected in a separate jar in that process. The next one is a very familiar one for you, which we have learnt already in 10th standard, electrolysis of sodium chloride. You remember, children, we take concentrated sodium chloride, which we call it as a brine solution, that when it undergoes electrolysis, we know at anode chlorine gas gets liberated. So that is another preparation where you use the electrolysis process. So these are the four basic preparation of chlorine. Now when we are studying about the properties, we already know that they absorb radiation or they emit radiation. So they are colored compounds, and the color of chlorine is greenish yellow, and they have a very pungent odor, and that is very much suffocating. Suffocating means you will not have a tendency to breathe comfortably. Now when we see the reactions of chlorine with different metals, non-metals, they react with hydrogen, they react with ammonia, they also react with sodium hydroxide, calcium hydroxide. Now the basic are, when it reacts with a metal, it forms its metal halides, like sodium combines with chlorine to form sodium chloride. They have greater affinity to react with hydrogen, forming the corresponding hydrogen halides. But when this chlorine reacts with ammonia, it forms ammonium chloride. But when it was combining with ammonia, if the presence of chlorine is excess, it forms a compound NCl3, which is an explosive, and that's a very highly dangerous reaction. So these are the basic properties. Now we will be studying about sodium hydroxide and calcium hydroxide property. The properties of chlorine: it reacts with sodium hydroxide to form sodium chloride and sodium hypochlorite, and also with water. And when it reacts with calcium hydroxide, it gives bleaching powder, that is calcium oxychloride along with calcium chloride. And the next reaction is a substitution reactions with hydrocarbons, which we have learnt in +1. It reacts with methane or ethane to form their corresponding chlorides, that is, it forms methyl chloride, ethyl chloride, and the reaction gets on continuously, chain reaction. Now this chlorine water, when it is kept for a long time, it tends to lose its color because of the formation of HCl and HOCl. It also acts as a very good oxidizing agent, like it can convert sulfur dioxide to sulfate, that is, the oxidation state changes completely of sulfur. So that is a very good oxidizing agent also. Some of the uses of chlorine are, it is used in bleaching wood pulp, in extraction of gold and platinum, in sterilizing drinking water. So in many areas chlorine is being widely used. Now we will get into hydrochloric acid, or we call it as hydrogen chloride. Now in 1648, Glauber was a scientist who gave an initiative to find this compound, but in 1810 Davy he found that this compound is nothing but a combination of hydrogen and chlorine. Now how was the preparation? When sodium chloride was treated with sulfuric acid, you get hydrogen chloride and sodium bisulfate. Now it's a colorless and pungent smelling gas. When it reacts with water, it can readily soluble in water. When it reacts with water, it ionizes to form hydronium ion and chloride ion. And you know the Ka value is very, very high. It also reacts with ammonia to form ammonium chloride, which we have studied in 10th standard in reversible reaction. If you remember, children, they combine from both the sides, forming dense white fumes of ammonium chloride. Now there is a compound called aqua regia, which is a combination of 3 parts of concentrated HCl with 1 part of concentrated nitric acid. So when these combine together, they form a compound which is called as aqua regia, which is used for dissolving the noble metals, especially like gold, silver and other metals. See, it also readily reacts with acids, weak acids, especially like sodium carbonate or weak salts, to form their corresponding halides. Like sodium carbonate reacts with HCl to form sodium chloride, water and carbon dioxide. There are many reactions. Under each heading you may have to study these reactions, children. At least remember what is the use of HCl. See, it is used in manufacture of chlorine, it is used in extracting glue from bones, and also in medicine and laboratory agent. When we come for oxo acids of halogens, I will be posting a video with oxo acids where you have 4 oxo acids: hypochlorous, chlorous, chloric and perchloric. Regarding that, the structure is important, which I will be sending a video which you will be able to understand better the structure of each acid. Now we will get back into interhalogen compounds. When we were studying about the chemical properties, we were discussing about halogens combining with halogens getting a positive oxidation state. Now, so here we will study in detail about interhalogen compounds. Now how they are prepared? Now when they are taken in equal volume or equimolar quantity, or one taken in excess, some 4-5 preparations are given. You can select any one of the methods. When it is being heated, what happens? You get the corresponding interhalogen compounds. An halogen combining with another halogen. If you see the property, they are very much diamagnetic in nature, that is no unpaired electrons. They are volatile solids and liquids except for chlorine, which is a gas. And these interhalogen compounds are more reactive than their halogens. This is an often repeated question in board. Why interhalogen compounds are more reactive? It is just because their bond is weaker as compared to that of a halogen-halogen bond. Example, ClF bond is weaker when compared to Cl2 bond. Here both are the similar atoms, here both are different. So this bond is weaker, so they can easily break the bond and react as compared to that of the Cl-Cl bond. And they can easily get hydrolyzed in water, out of which the smaller halogen, size halogen will form a hypohalous acid, and the larger anion will be forming a hydrogen halide. And if you see the structures according to VSEPR theory, valence shell electron pair repulsion theory, XX3 will be forming a bent T shape, XS5 will be forming a square pyramidal, and XX7, that is example IF7, will be forming a pentagonal bipyramidal structure. Uses, they are very good fluorinating agents, and they are also used for enrichment of uranium by forming a compound UF6. Uranium combines with the interhalogen compound to form UF6 and another interhalogen compound. So these are the basic uses of interhalogen compounds. Now we will come to the last topic of this chapter, which are group 18 elements. We will just go through the properties of group 18 elements, and hardly there are very less because they form the noble gas, and you know they are highly stable. So we will just go to group 18 elements. We will learn about group 18 elements. Now group 18 elements are called as noble gases, or you also call them as inert gases, which means they don't react at all. They are chemically inert. Now if you see, except radon, all of them are noble gases, and radon is present in the atmosphere. Now how radon is prepared? It is prepared by the decay product of radium. You get radon and helium along with it as a byproduct. If you see the electronic configuration, it has Ns2, Np6, having very high ionization energy because completely filled octet configuration. So you cannot remove an electron that easy when compared to other elements in the periodic table. Its atomic radii increases down the group, as we have already been studying. The number of shells increases. Electron gain enthalpy is positive value because it has completely filled octet, so it does not need any electron again, so it has a positive value. The physical property, it's monoatomic, colorless, odorless, tasteless, sparingly soluble in water. The interatomic attraction, what is the attraction that it has within its molecule, is a very weak dispersion force. And if you see the chemical property, except helium, all the other elements, that is noble gases, they have Ns2, Np6 configuration, and they are very inert to chemical reaction because of these reason that they have completely filled configuration and a very high ionization energy and also electron gain enthalpy. So because of these reason, they are chemically inert, or I can say they do not take part in the chemical reaction. We have some of the reactions now which we will be discussing now. Yes, we have come for the last one, forming xenon fluorine and xenon oxygen compounds. See, this is in different ratio, children. If you see the textbook, it is given 1:5, 1:20, 1:5, 1:20 ratio, where xenon combines with fluorine to form XeF2, XeF4 and XeF6. It is also prepared by treatment of XeF4 with O2F2 and forming XeF6. So these preparations, any one can be asked in the exam, forming xenon fluorine compounds. You can select whichever you want and you can write and mention approximately a temperature in the arrow. This xenon fluorine compounds, they actually react with ion acceptors like phosphorus pentachloride to form anion and cation complexes with XeF plus and PF6 minus. So this is a very important reaction, they may ask you in 1 mark, where xenon fluorine compounds react with ion acceptors. When you come to xenon oxygen compounds, in different methods are there: partial hydrolysis, complete hydrolysis. These are, the first two reactions are complete hydrolysis where the xenon compounds, they react with water to form the xenon oxygen compounds. Similarly, the next one is partial hydrolysis where only some of the compound get hydrolyzed and remaining there remain settled in the water forming xenon oxyfluorine compounds. Structures, if you see children, they have linear structure, square planar structure, square pyramidal, distorted octahedral and pyramidal. I will be posting a video where you can see the structure of XeO2, XeF2, XeF4, XeOF2 and everything, where the lone pair of electrons is mentioned separately. So, in the video you will be having a clear idea of how to draw the structure. So, you have to by heart the structure that is given in the textbook. You may not be asked to explain, you may have to just write the name of the structure and draw it. Okay, with this the class gets over and we will begin the next chapter in the next class. Thank you children. Xenon fluorides. The group 18, helium, neon, argon, krypton, xenon and radon are called inert gases. The inert gases do not undergo chemical combination with other elements or compounds due to their stable electronic configuration. However, in this group, xenon is an exceptional element as it reacts with other elements. The reason is it has a very low ionization enthalpy which makes it more reactive. The element with which xenon react the most is fluorine. That's why the compounds formed as a result of these reactions are called xenon fluorides. So, we are going to see the xenon fluoride compounds and the properties of xenon fluorides. All the xenon fluorides are solids, they are crystalline in nature and they are also colorless. The lower fluoride compounds of xenon form the higher fluorides when they are heated with a certain temperature and pressure. So, we will be seeing the preparation of xenon tetrafluoride and xenon hexafluoride now. Also, they oxidize the chloride ion to chlorine and iodide ion to iodine. The fluorides also undergoes rapid hydrolysis even with very little water. Xenon difluoride reacts slowly with water to form XeO2 and release oxygen gas. Xenon tetrafluoride reacts violently with water with the formation of XeO3, which is an explosive, and a release of oxygen gas. Xenon hexafluoride reacts strongly with water and undergoes a slow hydrolysis forming xenon trioxide. So, these are the reactions with water. Now, let us look at the molecular structure of xenon fluoride compounds one by one. First, let us start with xenon difluoride. The low electronegativity of xenon makes the xenon take a central position and the two fluorine atoms join the xenon. In the excited state, xenon forms 5 sp3d orbitals. Two of these sp3d orbitals overlap with one fluorine p orbital forming sigma bonds, 2 sigma bonds. The remaining 3 sp3d orbitals, which has a lone pair, arrange themselves in a fashion of symmetrical way, making a linear shape to the structure. These lone pairs will not affect the regular geometry of xenon fluoride as the net repulsive force is actually 0, being all the 3 lone pairs symmetrically located around the molecule. Hence, the geometry of XeF2 is linear. Now, let us take XeF4. XeF4, again the low electronegativity of xenon when compared to fluorine makes it take the central position, and in the excited state it forms 6 sp3d2 orbitals, and 4 of these overlap with 1 p orbitals of 4 fluorine atoms forming 4 sigma bonds. The remaining 2 sp3d2 lone pair arrange themselves opposite to each other, making the shape to become square planar. In this case also, the lone pairs of the geometry will not affect the original shape as the net repulsive force is 0. Hence, xenon tetrafluoride takes a square planar shape. Now, we will get back into xenon hexafluoride. Again, in case of xenon hexafluoride, you can see 6 fluorine atoms arranged around a central atom xenon, as xenon is less electronegative than fluorine. In the case of the excited state, there are 7 sp3d3 orbitals. 6 out of these will overlap with 1 p orbital of 6 fluorine atoms forming 6 sigma bonds. So, you can see the sigma bonds formed around the xenon with 6 fluorine atoms. There is remaining 1 lone pair which lies between a bonded pair of fluorine atoms. This odd position exerts a repulsive force and makes the geometry little bit distorted, and hence xenon hexafluoride forms a distorted octahedral shape. In this case, the net repulsive force is not 0. Now, here you can see the bond pair electrons, the lone pair electrons, the hybridization and the shape of the xenon fluoride compounds. And this is a summary of xenon fluoride compounds.